we just tried everything. We just tried it. Okay.
That's dimmer.
Okay, this will do. I think.
These are generally better than these. Right?
That's too much. Yeah. That's too much. I think go back.
How's that?
Maybe a little bit higher.
I think that's part of the sort of fluorescence.
Okay, I'll live with that.
Otherwise it's this one, right?
No, I want to do a little bit though. Yeah, that's good. That's
Okay.
good. I'm gonna start at 2:30.
I'm going to introduce you, Steve.
No.
Yes.
No.
It'll be 20 seconds.
Okay. I'm gonna.
Okay, so I'm going to give the shortest introduction possible.
Yeah, thanks.
Because I've been instructed by the speaker that I cannot take a single moment of his time. We have to finish exactly at 3:20 because another class comes in. But immediately after the lecture, everybody's invited up to the live lab for some lessons and folk dancing. Line dancing, right?
Yeah.
I've done it before with Stephen. It's a lot of fun. It's excellent. I suggest you all do it. It's 2:30. Everybody welcome Stephen Brown.
Okay, thanks. No, sorry about the rush, but my talk is really sort of 45 minutes, and we have to be out of here at 3:20. Okay, so my talk is called Scaling and Beating, the Distinct Evolutionary Trajectories of Pitch and Rhythm in Music. And so most of the ideas that I'm going to present here are published in a book that I published last year called The Unification of the Arts, a framework for understanding what the arts share and why. And so most people agree that music has two basic dimensions, one related to pitch and one related to rhythm. So the one about pitch is about things like pitch classes, intervals, scales, melody, harmony, and the like. And the one about rhythm is about timing, duration values, tempo. We'll talk about this notion of interpersonal synchronization that we call entrainment. The accepted models of both musical scales and rhythmic entrainment in the literature are completely asocial. And this is really paradoxical because most people think about music and dance as being kind of the pinnacle of interpersonal coordination, synchronization, reflecting our deepest social side. But the theories that you see in textbooks about the basis of scales and rhythmic entrainment are completely asocial. So I want to propose alternative theories to the standard models. And so I'm going to start with scales, and then I'm going to work towards rhythm and beating. So this part of the talk is called Scaling, the Vocal Motor Origins of Musical Scales. And so the ideas behind this section of the talk were just published in a very short, this is a 5-page paper, so if you want to kind of get these ideas really quickly, this is a paper that Elizabeth Phillips and I published a few weeks ago in Frontiers called The Vocal Origin of Musical Scales. This is the model that we're trying to propose as a replacement, called the interval spacing model. So again, 5 pages if you want to get a quick and dirty view of the information from this part of the talk. And so the standard view of the origins of musical scales is that if you think about sounds that are pitched, like my voice, they don't contain just a single periodicity or frequency, but a whole family of frequencies that are related to the fundamental as integer multiples of the fundamental. So I'll show that here. So this is referred to as a harmonic series. So if this note is the fundamental, then the second harmonic is twice the frequency of the fundamental, the third harmonic 3 times, the fourth harmonic 4 times. And so it was noticed a long time ago from the time of the ancient Greeks that if you look at these kind of ratios, like 2:1, 3:2, they establish basic musical intervals. And so, for example, 2:1 corresponds to what we call an octave in music, 3:2 makes the perfect fifth, 4:3, etc. And so you can take all these perfect ratios and kind of plop them down to create a scale. So here's a representation of C major scale, where here's the fundamental, here's the octave at the 2:1, here's the fifth at the 3:2, the 4:3 makes an F, etc. And so these can be thought of as being, kind of natural scales. They're given to us by the vibration modes of vibrating objects. And so they're all based on physics. They're all based on these nice, perfect mathematical ratios. So it's as if musical scales are given to us not so much by biology, but they're given to us by nature and by physics. And so I'll refer to this as the harmonicity theory of musical scales. And again, if you look at textbooks on music and psychoacoustics, this is the dominant model of where musical scales come from. They come from these harmonic ratios of the harmonic series. And so this is a pretty good theory about perception, and features about the auditory system definitely conform with this harmonicity. But it really begs the question for us as humans, that how does some perceptual capacity magically lead to the motoric capacity to create musical scales? And so this is a big mystery, and the harmonicity theory really has nothing to say about production. And so if scales are given to us essentially by nature, by acoustics, then why aren't musical scales widespread in animal species? They're not. And why isn't human speech based on musical scales? It's not. Okay, so just talking about this kind of mechanism really begs the evolutionary question, well, how do we develop this motor capacity like I have right now to be able to produce musical pitches? And so the key question is how we came to evolve the capacity to produce stable level tones that we call pitches, and stable transitions between those levels that we call intervals, compared to a bunch of slides and glides that pretty much characterize the way that most mammalian species vocalize. In other words, how do we arrive at creating some kind of digitization of pitch space to create these discrete levels that we call musical scales? And again, the harmonicity theory doesn't even consider the issue of production, but this is a really key evolutionary question for music. And so I'm going to frame this in terms of changes that occurred evolutionarily to our laryngeal system, to the larynx itself, and to the parts of the brain that control the larynx that allow us, not uniquely, but rarely among other animal species, to create level tones and level transitions. And so to talk about this, we have to talk about the vocal brain, and I have a little bit of a sore throat today, so excuse me. So just a reminder, when we talk about the larynx, we're talking about the organ of vocalization here. So if you think about where your Adam's apple is, it's pretty much where your larynx is. It houses these two pieces of fibrous tissue called the vocal cords or the vocal folds, which when set into vibration by air coming from your lungs, produces the basic pitch of your voice. The next slide shows the classic homunculus of the primary motor cortex of humans, derived from the work of Wilder Penfield and his colleagues in the 1930s at the Montreal Neurological Institute. And so we see pretty much all the effectors of the body along this homunculus. For the face area, we see the lips, the jaw, the tongue, but there's no larynx. There's no larynx in the Penfield homunculus, and if you read his books, he says that he wasn't able to get reliable localization, which is why you see vocalization kind of smeared across the full extent of the motor cortex. So during one of my postdocs, I wanted to address the question, where is the larynx localized in the human motor cortex? So kind of as a sanity check, I wanted to use tasks that would engage effectors for which Penfield did show reliable localization. So I had people move their lips, move their tongue, but I also wanted to do a bunch of laryngeal tasks. So I had people reading out loud, I had people singing, and I had people doing other laryngeal tasks that were not vocal. The right side shows a schematic of the results, and so I was able to replicate Penfield's localization that the lips are indeed dorsal to the tongue. But where's the larynx? In the motor cortex. So I found it here directly adjacent to the lips, and if you look at the left side, which is the actual brain data, there were two peaks, one in the primary motor cortex, a second in the premotor cortex. And so I gave this area a name, and I called it the larynx motor cortex. And this was published about 15 years ago, but since then, this has been verified as being, this is the vocal center of the human brain. It doesn't matter if we're speaking or singing, this is where the voice is in the brain. But there was more to the story than that in the original publication. What about phylogeny? What's the situation about the larynx motor cortex in non-human primates? It's quite different. And so the larynx motor cortex in monkeys is not important for vocalization. Lesion in this area has no effect on vocalizing. So the typical things, you take the monkey before surgery, you look at what's the rate it's calling, you look at the spectral features, you do the surgery, let it recover, and then again, what's the rate of calling, what are the spectral features, and there's no change. And so there's a larynx motor cortex that controls the laryngeal muscles, but it is not important for vocalization. Lesion, it doesn't really have an impact on vocalizing is typically subcortical areas that are important for vocalizing in non-human primates. But there's more of the story than that. Is also about the localization. So here's where I found the larynx motor cortex. The purple is the primary motor cortex. This is a human brain, but if we were to put the monkey area on the homologous part of the human brain, it would be there, in the premotor cortex, not in the primary motor cortex. So in my original publication, I said there's been some kind of reorganization of the human brain, some kind of restructuring that's led to a migration of the larynx area from where it is in non-human primates to where it is in humans. So I just said that the human larynx area has undergone a change in location compared to non-human primates. So I basically argued in this paper, and it's not been disputed yet in 15 years, this is a novel part of the brain, a novel human-specific part of the brain that confers on us the ability to vocalize the way we do, including level tones and level transitions. And so this change has been accompanied by a transition from the non-vocal functionality of the monkey to now this area is very important for vocalizing. When people have strokes here, it really impairs speech production. So a big change in the functionality with this reorganization of the brain. And so as a speculation, but again, this has not been disputed to date yet, this area has allowed humans to evolve both speech and song. So again, I've discovered not just the larynx area, but there seems to be a novel human-specific area that's conferred on us the ability to vocalize the way that we as humans do, both in terms of speech and song. So this first paper came out 2007 online, and then 2008 in print, so a larynx area in the human motor cortex. And in my own head, for me, this was a game changer for the music field. I discovered this new area that I said, okay, confers on humans the ability to produce vocalization the way we do. And I thought that was going to really be a big change for the field. And I can say a little bit sadly that in 16 years, the music cognition, neuroscience, and music field, this is not on the radar at all in music cognition. And so it's a little bit disappointing. The field is very much focused on the auditory system, auditory perception, and so the whole evolutionary idea about where those pitches come to begin with to stimulate that auditory system is really not on the table in the field. So what I'm thinking now is that maybe after I die, maybe someone's going to rediscover this work and promote it. But for now, it's really not on the radar. Okay, so I've talked about the brain, but now I want to talk about, even if we look at the end effector of the larynx, in humans the voice is a very imprecise instrument, and so all these harmonicity theories are based on instruments that you can tune very precisely, so strings and pipes. But if you look at the voice is actually very much imprecise compared to these engineerable, tunable instruments like violins and flutes. So here's a study that Peter Fordresch and I published 6 years ago, and so this is from a group of 37 sort of people like us, so people who are amateurs but who can accurately sing, not tone-deaf people, but also not people who have gone to the conservatory, just sort of run-of-the-mill accurate singers who are not professional. And we had them sing the song Happy Birthday, and so these are the 4 smallest intervals. ST stands for semitone. If you don't know the cent scale, 100 cents equals 1 semitone, so these are basically semitone increments. As you can see for these intervals, that the distributions are very, very wide, spanning several semitones around the target. And so this is for people like us. And then we also looked at professionally trained opera singers, and the situation is better. But again, you can still see there's at least a semitone of error around on either side of the target pitch. And so we refer to these distributions as interval islands. So again, it's not these perfect 3-to-2 ratios we get from harmonicity, but there's a lot of noise built in to this vocal system. So we talked about intervals. They're actually islands of frequency, not these perfect ratios. So then when Elizabeth Phillips came to the lab, I said, okay, we've done this for Western people for one song. Let's now take this on the road and do a global analysis. And so this was published last year, this article, Vocal Imprecision as a Universal Constraint on the Structure of Musical Scales. And so we created a corpus of 418 ethnographic field recordings of indigenous singers singing solo vocal songs. And one thing that's really new and exciting is how we did the sampling. So if you look at the colored groupings of this map, this is not ethnic groups, this is not linguistic groups. these are music families. These are the 10 major music families based on the work of Alan Lomax in the 1960s, the Cantometrics project. So this is really a representation of our sampling of the 10 major music families, trying to accommodate the diversity of scale types and singing types in the world. So really, this is the first study of its kind, and I hope this will be sort of the model of how cross-cultural music studies proceed after this. So here's an analysis of one of our samples. It's a Siberian song, and so you can see pitch again, 100 cents is one semitone. Here's the time axis, and so here's what the song sounds like.
Soroje, soroje, andhasali, soroje, 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 soroje.
So it just repeats after that. So we just looked at that first phrase, which is like 12 seconds, and again, this is a mellograph. It shows the pitch across time. So along the top and along the side, you can see the scale series. So it's a 5-note scale. We've tonicized all our samples. So in this case, A is tonic. The F sharp, which is sung, is subtonic. And then we have 3 pitches above the tonic. And so to get a sense of the imprecision, we looked at these bands, the width of these bands as a measure of that. I think Elizabeth was really hoping this could be done all computationally, but it didn't work out. And so all these bins, you see these white bands, are defined by hand, by her and her students. And so we can look at the width of those bands as being, again, an indication of the imprecision. So this is shown for each one of the pitches. And then we get a mean of 1.15 semitones as being the average imprecision for this one song. What happens when we look across the world, across the 418 songs, and this was actually 2,400 pitches that were analyzed by Elizabeth and her students. And so the mean pitch class imprecision for the global sample came out to be 1.5. So slightly larger than the last song I showed you. 1.5 semitones was the cross-cultural mean. And from that, we can explain a lot about musical scales. Okay, so think about the first one, so the minimum step size. So pretty much everyone agrees that 1 semitone is the smallest reliable unit of musical distance. Yes, there are traditions like Indian classical music that have microtones that are smaller, but they're thought to be idiosyncratic, and that 1 semitone is kind of the lower limit for a reliable unit of musical distance. It's not so far from this. What's the comparable number for perception? If you look at the just noticeable difference for frequency perception, the threshold is 1/30th of a semitone. So this value is much, much closer to a motoric limitation than it is to anything related to perception. What about the number of scale tones? So in music, an octave is 12 semitones, so 12 divided by 1.5 said there should be an upper limit of 8 or so pitches per octave, and universally scales are found to have between 5 and 7 pitches. In our corpus, the value was found to be 5.5 pitches per octave. What about this? What about the inventory of step sizes? So the next figure shows the intervals between adjacent pitches, adjacent scale tones in these samples. And so the mean scale interval spacing was found to be 2.2 semitones. So I said kind of the noise of individual pitches is around 1.5. The actual observed scale spacing is even larger than that. It's 2.2. In music, we call 2 semitones a whole tone. So the whole tone seems to be not just the most common interval in music cross-culturally, but something of this optimal, like a baby bear thing, that it's beyond your noise for pitch classes, but it's not so large that it really is going to tax your vocal system. So our basic story is that the structure of musical scales, scales are trying to optimize pitch spacing based on the intrinsic imprecision of vocal production. That's our interval spacing model of musical scales. Looking at this again more musicologically, more categorically, 90% of these scale intervals are made up of just 3 different types of intervals. So a semitone is 1 semitone, 2 semitones is the whole tone, 3 semitones is called a minor third. And so again, 90% were made up of just 3 step sizes. In other words, a whole tone plus or minus a semitone. Okay, so it turns out to be a relatively simple kind of system for building up scales. Just 3 interval sizes make up 90% of scale intervals. So I can't say strongly enough that none of this information is ascertainable from the harmonicity theory. It explains nothing about this. The vocal theory sheds light on pretty much the key fundamental features of scales. The The harmonistic theory says nothing about step sizes, scale tones, nothing. So this is, I think, a big advance in thinking about the origins of scales. So I talked about this larynx motor cortex, and then moving to the level of the larynx, that we have this intrinsic imprecision, which is constraining the structure of musical scales. So the standard theory in music is this top-down theory that we take all these harmonic ratios and we put the 2-to-1 there, 3-to-2 there, whatever. Can we think about building scales now from the bottom up rather than this top-down harmonicity interpretation? So one thing about this model is that it kind of predicts that this 7-note scale kind of emerged all at once. Like, it's all about the harmonics, so, they just came all at once. I think that's a really bad theory. And so if we think about this more vocally, it's kind of just a big challenge to create these steps. And so I think we have to think the scales, if the idea was to digitize pitch space, probably started out with small, like 2-note scales, and kind of worked the way up. And in our corpus, I think it was 12% of the scales were between 1 and 3 notes, and these were definitely found in the most indigenous, the most tribal groupings in our corpus. But how do we build scales from the bottom up? And so for this, I'm trying to revive a long-forgotten theory put forward by the musicologist Kurt Sachs in the 1940s. And so Kurt Sachs said we can build scales from the bottom up using 2 mechanisms that he calls affixation and infixation. Again, this is something that people don't read about these days, but I've read his work for a long time, and so this idea kind of resonates with me. So one way is through affix. So starting with this 2-note scale, we can affix a pitch to one end or the other to make the 3-note scale. So I've shown the affix as being at the top. Alternatively, he says we can create an infix. We can start with the same 2-note scale, and now we can insert a pitch in the middle. And whether we build the scale through affixation or infixation, these kinds of spacing principles have to hold, that a whole tone should be something of the optimal spacing. So we have to, whether you're doing it this way or that way, the insertion or the addition has to abide by this vocal imprecision. So basically we're arguing for a bottom-up theory. Essentially a generative theory says, we have 3 or 4 basic units, and we just combine those in different combinations to create all this magnificent diversity of scales. And so Sachs talks about the kaleidoscopic diversity of musical scales. And so again, using a few basic pitch steps, we can combine and recombine them to create a huge amount of scale diversity. So to kind of summarize the first part of this talk, so what a vocal motor model of scaling gives us compared to the standard psychoacoustic model based on harmonicity. One is as grounded in vocal communication, so it's intrinsically a social model. It's not just about the physics of vibrating bodies. It takes seriously this evolutionary issue of how do we come motorically to create level tones and level transitions. I've argued that the larynx motor cortex was a key evolutionary step for that. The model can predict the size and intervallic spacing of properties of scales. It's a progressive model that argues the scales evolved from small to large, which I think is quite reasonable. It's a generative model that can account for the diversity of scale types cross-culturally. I didn't get a chance to talk about this, but humans also are somewhat unique in being able to engage in vocal learning and imitate, and so this is definitely connected with the story about the larynx motor cortex and the new connectivity that emerges with this new area, that we learn the sounds of our language from conspecifics, we learn the pitches of our scales through learning mechanisms from conspecifics. And then finally, a really burgeoning field these days about the coevolution of music and language or of speech and song, including the universal combination of vocal music with words. So now I'm going to switch gears and talk about the second topic about rhythm. So beating, so the interpersonal origins of rhythmic entrainment. And so most of the ideas about this were published last year in this article called Group Dancing as the Evolutionary Origin of Rhythmic Entrainment in Humans. So I'm gonna say, I see John here, with apologies, because this is, you all know Snowball. Snowball is this sulfur-crested cockatoo who's essentially the best dancer, the best non-human dancer that we've all seen. In fact, this video is not going to even show kind of the choreographic richness of this cockatoo. This is taken from an experimental study. John was part of this. I'm going to take a critical stance, but it's not the way you're going to think. I think this is amazing, but I want to think about this in terms of evolution. I think there are limitations. So I'm going to talk about the dancing animal model as being kind of the default model for the people in music cognition. So I think you've seen something. Okay, so that's Snowball, the cockatoo. And so, again, I want to say that, this is the most spectacular example of dancing, not just this video, but other videos. I mean, it's like this big repertoire of movements. It's very impressive. And just like John, I want to understand what is it about Snowball's brain that allows him to do this. So don't get me wrong for the rest of the talk what I'm saying. But I think, yeah, we're not going to be friends after today. That's clear. So these dancing animal studies show the amazing ability of certain animal species to entrain to a rhythmic acoustic beat, as we just saw. But it begs the question, who's serving the role of the Backstreet Boys that we just heard for cockatoos? And to the best of my knowledge, the answer is no one. And so it begs the question of who's generating this capacity for rhythmic entrainment in the wild. And to the best of my knowledge, people can correct me if they know better, but to the best of my knowledge, the answer is nobody. So it becomes kind of this amazing latent ability of cockatoos to entrain to music, but there's really nothing in their own ecology that kind of sets up this relationship. And at a more general level, pretty much all theories in the field about the origins of rhythmic entrainment are two-stage models. So first, music evolved, and music gave you the beat, and then at some point, someone said, yeah, I'm getting it, yeah. And then dance evolved as a second major transition. But there are all these two-stage models which said that music had to come first, music had to give you the beat, and then one day someone just said, yeah, that feels good, I'm gonna move to it. I kind of show this in the article this way as the music first model, that as far as the source, what's the cue for entrainment? So first, musicians evolved, they provided the rhythmic stimulus to which other people, a second evolution, the dancers, then started to move to it. So it's a two-stage evolution. So I'm going to present an alternative model now in which music has no role whatsoever. This will be a music-free model of the same phenomenon, but it doesn't rely on music. It's going to be a very different kind of model for the origins of this same phenomenon of entrainment. So to get started, we have to distinguish two different forms of entrainment. So if you come to my wineless and cheeseless wine and cheese afterwards, I'll be using this laptop to play music, and so I'll teach you some steps, and I'll say, entrain your steps to the beat, but that's completely external to you. So just like with Snowball, the source of this entrainment is coming externally to the people who are doing the entraining, but we can entrain to one another, we can entrain mutually, so we can entrain externally, but we can also entrain to one another. And so this becomes really critical in thinking about this alternative model, because the standard model is very much music-induced movement. There's music and that induces movement, or musical groove ideas. They're all the same thing, that the signal is external to the people doing the entrainment. So if I had to pick one video, as an animal video as being the best model of it, it'll be this one. And this is really a crappy cell phone video. It's not a professional thing at all. So these are two captive chimpanzees, females, living in a zoo in the US. And so if you look at the title of the YouTube video, it says, two chimps walking in a conga line. Okay, so you're going to see very, very entrained walking in between these two. And let me switch to this one. I may turn the sound up because the voiceover from this is so ridiculous. Okay, I'm going to actually turn off this family talking, but they're holding something, I forget what it is, a bale of something. They're letting it go, they're sitting. But this is not the good part. The good part is when they're doing the conga line movement, which is they're going to start doing it again. They're going to lift up this bale of something and come on. Do it. Okay, we're going to get up now. Let's go. Okay, I'm going to stop. I'm going to just make sure that my sound is back on. Okay, I can get rid of this. Okay, so I say take note here. There's no music here. My colleague, I forget the first name, but the last name is Lamera. They've done an actual analysis of this and shown that these are totally synchronized. And then Granger, causality, the whole thing. So these two animals are very synchronized when they do the walking. So there's no music here. There's no external cueing of any kind. Instead, what you find are very, very strong. And I forgot to mention this. So the back animal, she puts her left arm on the shoulder. So there's a haptic connection between, I forgot to mention that, but you can see that in the video. So again, there's no music. There's haptic coupling, physical coupling between the animals. The back animal is able to visually couple with the front animal. And the next thing to me, I think is going to be very important, but I can't say for sure, but I'm going to speculate that the fact that they do this in the bipedal stance is going to be really key for this, because when they're just sitting around, they're swaying, they're out of phase, but when they get into this kind of bipedal thing, now they're totally synchronized. So I think something about bipedalism is going to be really critical for this, for the evolution of entrainment. So this leads to a very different kind of model that I've called the group dancing model, which says that the origins of entrainment, it's not about these external cues like music, but about interpersonal cues coming from mutual entrainment. In this case, the people who are participating are both the source and the effector, and it's the mutual entrainment that leads to their ability to synchronize. So this is a very different kind of model than this external pacing by music, the musical groove idea, which is very dominant in the field. In addition, this is very much a locomotor model, which says that our ability to entrain is not unrelated to the fact that we've acquired bipedal locomotion. One big advantage of this model, I think, compared to the music model, which only permits sort of, again, is music-induced movement, so only the auditory system comes into play. This model now allows for 3 sensory modalities. So maybe, David, you should be really excited about this. So it, of course, allows for acoustic cueing, although I'm going to say it doesn't have to be connected with music at all, so I'll talk about body percussion in a second. It allows for visual cueing, and what's really important is that this is now a moving object. So people have shown that if you entrain to a static visual signal, entrainment is not very good, but as soon as the thing is moving, then entrainment becomes much better. So if you're interacting with people, that's going to be a moving object. And then we and others have shown that haptic contact is as strong a cue for entrainment as music or anything else. And so potential for 3 different sensory modalities now to contribute to entrainment rather than just a purely music-based acoustic model. Okay, so you probably don't know this, but this semester I'm teaching a new course, 4th-year course in cultural evolution. And so pretty much every theory about the origins of human culture said that our ability to have culture is directly related to the fact that we've developed a very enhanced ability to imitate that allows us to learn from others, to teach, and therefore to transmit information to others. And so Merlin Donald talks about ancient rituals as being group mimetic acts, and that coordination is a kind of conformity. This is the kind of model that I want to use. I don't want to replace the musical group model and say that this entrainment is essentially about group mimesis, about learning how to imitate each other, because as a result, we become more similar to each other and more different than that competing tribe who has different kinds of rituals. And those between group differences are thought to be the major driving forces for the evolution of cooperative traits, sociality, as well as things like warfare that lead to big changes in human demographic structures. So hunter-gatherers live in groups of 100. We live in multi-million person cities. And so these kind of dynamics about imitation are thought to be really critical for how we evolved cultural capacity. So this is a very different way of thinking about this, that entrainment, group dancing, is essentially a form of group mimesis that allows us to be more similar and to be more different than competing groups. So this is a new idea, but I think this has so much potential because it really dovetails with the cultural evolution of culture literature as well. To the extent that acoustic cues are important, I think they don't have to be musical at all. They can just be kinds of body percussion. So things like leggings and rattles are found pretty universally across indigenous cultures. And so I want to give an example of this, just a short video of traditional Aztec dancing. So the Aztec dancers, they wear these leggings called chachayotes, and they hold rattles. And so you're going to hear a drum, which will be kind of the external signal, but you can also hear all the body percussion that occurs with their own dancing. stop it here just because of time constraint, but you get the idea. So there's a wide diversity of body percussion. So I'll think about this as the body itself and things that we attach to the body and 4 different regions of the body. So in terms of the sort of head region, again, for vocalizing, we don't have to be singing. If you've ever seen like these Maori warriors, they go, they're grunting or screaming. And so you don't have to be singing pitches. You can vocalize as a cue for entrainment without singing or using music in any way. It could just be grunts and screams. Necklaces can be used in this region. For the core, gorillas engage in body beating. You don't have to look much further than Canadian First Nations to see how people attach sort of sound-generating things that clank to their regalia to make them create sound as they're dancing. For the hands, I can't clap now, we can clap. Rattles are very, very common. And for the legs, they're stomping. And again, leggings and rattles are quite, maybe not universal, but very widely distributed among traditional cultures. So here's kind of the newest phase of my theorizing about this, just in the last year or two. So I realized that all these implements that are used for body percussion, they all contain some form of beating. And so I've been kind of looking at the history of beating. And so I call this new hypothesis, beating for beating. And if you look at the evolutionary literature, beating in human cultures goes back at least 100,000 years. So the use of marine shells to create beads, necklaces go back 80,000 years in human evolution. And so I kind of said this. In the archaeology literature, this is always talked about as being a form of ornamentation, display. And again, I have no evidence, but I'm convinced that this also had to be used for body percussion for tens of thousands of years to create these kinds of implements. And again, I don't know what kind of evidence I can bring up to verify this, but to the extent that things like necklaces have been around for 80,000 years, I just think that these kinds of things were also used as body percussion, whether it's the legs, the hands, whatever. But it's going to be a long time before I could give more evidence to back this up. So to think about these theories about the evolution of rhythmic entrainment, so the standard model, again, the dancing animal musical group model, basically is an asocial model based on the individual, on sensory motor skills in the individual. It only allows room for auditory cueing. It's based on external entrainment and doesn't make any kind of specification for effectors. The alternative I'm proposing, which is the group dancing model, places the focus exactly where it should belong in terms of group social cognition, social interaction, groups of people interacting with one another. It allows for multisensory cueing, those 3 modalities. It's based on mutual beat generation. It's very much a locomotor model grounded in bipedalism. And so when I showed the snowball video, I talked about this fundamental disconnect between the ability of some animal to dance very beautifully, but in terms of its own natural ecology, who's the Backstreet Boy there? And so I think the group dancing model essentially solves this mystery by saying that the entrainment signal and the entrainment behavior are essentially the same thing. It's all based on mutual entrainment. You can generate sounds, other kinds of cues through that interaction. So I feel this is an advance in theorizing about the origins of entrainment. So what about the dance-music connection? So I've argued here in my writings that the ability to synchronize with others to entrain evolved not in music, but evolved as a body sense through dance. Now, I haven't had the chance to talk about other things, other theories that I have, but I propose in my early writings that the music initially began as a kind of asynchronous coursing, kind of like a pack of wolves, where people are making kind of the same kinds of sounds, but it's not synchronized. And that later music evolved the capacity to synchronize and create synchronous choruses. And so the basic point I would get across here is that music evolutionarily co-opted dance's rhythmic systems. That rhythm began as a body sense through dance, and then somehow the vocal system that creates music was able to co-opt that system. But a really important caveat about this is that whatever this was that led to this co-opting, it can't just be a sensory motor thing, music-induced movement. It has to be as much about social cognition as about, of course, sensory motor skills are important, but it has to be about our general inclination to get together, to assemble with people, form attachments, theory of mind, whatever. It cannot be just a theory of like a finger tapping thing. So sensory motor capacities are indeed important, but whatever this is that allows us to entrain has to engage our social brain as much as things about music-induced movement. Okay, so let me just summarize. So I talked about the distinct evolutionary trajectories of pitch and rhythm in music. So I've argued for the vocal origins of musical scales, the body origins of rhythmic entrainment. I opened my talk by saying that the accepted models of both musical scales and rhythmic entrainment are completely asocial. And so these were the harmonicity theory for musical scales, the dancing animal / musical groove model for rhythmic entrainment. And so what I'm proposing as replacements are this interval spacing model that I'm working on with Elizabeth that is grounded in vocal communication, and this group dancing model, which is intrinsically based on interpersonal interaction, mutual interaction, social cognition, and the like. And thinking, coming back to this social imitation perspective, humans have evolved not one, but two major systems for imitation. On the one hand, we've evolved the capacity for vocal imitation and vocal learning, which is about the voice. This allows us to learn the sounds of our language and the pitches of our musical scales. On the other hand, we've evolved a separate system for gestural imitation in the body, which allows us, again, to transmit information culturally, and which I've argued that interpersonal entrainment essentially is an act of group mimesis, first and foremost. If there's sort of an overriding unification here, it would be about bipedalism in our species. So bipedalism has led to changes not just in our posture and the way we move, but also very significant changes in the structure of our vocal tract, which, thanks in part to this larynx area, allows us to create musical scales. This kind of a change is very poorly understood at the brain level, but this body sense would lead to beating. And then I've argued that musical rhythm is kind of a byproduct of those two. Okay, I really rushed, so I'm going to get done in time because I was just rushing through this. But I do want to give a big thanks to my amazing lab members for discussions, but also attempts to empirically test these ideas. So these are my current grad students. Matt Berry has left, but he's forever the conductor of the train of my lab. Yeah, just a reminder that I'm going to be hosting this wineless and cheeseless wine and cheese. So it's going to take place, so the dance studio is actually in this corner of the building. It's not the main theater, it's this corner here. And I don't know how many people are actually coming. I just want to say that it's quite a small room. And so if you're coming to dance, great. If you're coming to watch, I think there's not going to be a lot of room for watching because I've tossed sort of 30 people there. And so if more than 30 people come, it's going to be very crowded. So if you're coming to dance, we'll make it work. I think observers, there's not going to be a lot of room to have people observe. Anyways, I'm finishing on time because I really rushed my presentation to be done in time. But I think there's going to be 5 minutes for questions, which is good. Thank you.
Excellent talk, thank you.
Thank you.
So we have time for some questions. John?
Yeah, lay it into me. Lay it into me.
No, I want to say we're still friends.
We're still, okay, let's be friends. Let's stay friends.
So the snowball, that paper was kind of very artificial, as you noted, right? We were trying to take away as many cues as possible to see if snowball could still synchronize just with music, right? But in fact, the natural behavior of synchronization for snowball was entirely social, right? He, grew up dancing with his owner, right? And so we have a study we call Dancing with Myself because we were playing the Billy Idol song, and we compared how much Snowball danced when there was music alone, with no one in the room, no one watching, music with his owner encouraging him, and then music with them dancing together. And as you predict, it was all about the social.
But you get my point that the real question is about the ecology of cockatoos, not about this, a captive. No, I get your point. I know all about the owner and how she really kind of induces this. So obviously there's a visual component clearly to his imitation.
Yeah, so I mean, the real question was does an animal have the capacity to do that? Whether they do it,
But you get my question, like who's the Backstreet Boy analog in the wild for cockatoos? And as far as we know, there isn't one.
Well, I mean, so the theory was that like there doesn't need to be a Backstreet Boys analog. There needs to be some kind of vocal imitation of vocal learning.
Some kind of,
Vocal imitation of vocal learning.
why?
Because that leads to connections between the auditory motor system that enables this kind of close feedback to do timing between sound and music, between sound and movement. That was the idea.
Okay. We're not going to be friends maybe in the end, but we can try and keep it going.
I think you're kind of misunderstanding because I don't think I don't disagree with anything you said.
I'm kidding, of course. Yeah.
Pat?
I'm just curious about the vocalizations. If you made a recording, with a computer or something that lacked that sort of variability, and but use a natural human voice, if you could do that, would it sound weird? Would it sound really nice? I mean, would people be able to tell the difference? I mean, does that variability add anything to?
I mean, aside from voices, I mean, you know what a pure tone sounds like, which is a single periodicity. So, I mean, there are obviously ways to filter the voice to remove harmonics. I can't give you a definitive answer what they all sound like, but we all know what a single frequency sounds like as a pure tone. That's kind of the limit, right?
Sure. So if you recreated a song without that variability that people have as they're going through the song,
Yeah.
if you got rid of the noise, it would just sound like, are you saying it would just sound like a bunch of pure tones?
No, I mean that's.
Would it sound odd, or would it sound just the same as a?
Well, I mean, every person's voice is a different timbre because it has a different distribution of harmonics. So, you sound different than me. So you sound weird, and I sound normal, right? So, no, what I'm saying that I can't give a definitive answer because I haven't spent a lot of time filtering the voice. But it's possible to filter the voice, and it'll still sound like a voice as opposed to a pure tone. But obviously, we're looking at what the features of the voice that are naturally occurring. We're looking at indigenous singers, so it's less about an experiment as what are the features of the voice in the wild, in natural settings. So I get your point, but I think you can filter the voice. It'll sound like a timbrely different voice. I think is my suspicion, but it'll still sound like a voice and not like a clarinet. I think.
But man, I think you might have been talking more about auto-tune.
Well, auto-tuning, for example. Yeah, I mean, so that's an example where you're playing with the.
Like you make all the pitches perfect when it sounds.
Yeah. Okay. So was that your question? So that's a good answer. So auto-tuning is a way to kind of perfect those distributions.
I mean, because when I listen to auto-tuning, I'm thinking, God, that sounds odd.
Okay.
It does not sound like a natural voice.
Yeah, no, I think you're right that it will sound less natural than the natural imperfections of the voice. Yeah, Paul.
Stephen, I don't understand fully your argument, but I'm not sure about the bipedalism part here, because I'm thinking about, in terms of the evolution of entrainment, why isn't a mating system is a great example of how you can get a natural, it's a social thing, mating, usually, and you can have antiphonal calling systems. There are insects that are doing this, there are birds, there are mammals. They're not necessarily bipedal mammals, of course insects aren't bipedal. So I'm not sure, why couldn't entrainment evolve under a mating, ritualistic context?
So when we talk about entrainment, kind of in our context, we're talking about synchronization to a beat. So that's kind of what we're talking about. So rhythmic. So I know you're talking about there's lots of entrainment, but it's not rhythmic. So you talk about antiphonal calling. It's not going to be sort of a metronomic kind of a thing. It's going to be more irregular. So then you have like insects, whatever, who have sort of metronomic calls. They have isometric calls, but they're not. And so if you think about like crickets and frogs, they engage in entrainment, but it's not the cooperative. We weren't talking about that, were you? It's not the cooperative kind.
They're calling antiphonally, or they're calling to lead. To be
They're calling to
first
lead.
in the signal.
Yeah. So it's
Therefore, they have to entrain in order to do
yeah.
that. I'm just saying mating is a context in which, it's a social context in which you could get the evolution. I don't know if bipedalism is a factor there.
So definitely I'm talking about the entrainment of movement and less about the entrainment of, so I totally get what you're saying. There's the entrainment of vocalization, but in the music field, people are talking about the entrainment of movement to a beat and how we're able to, like in a discotheque, synchronize to the beat. And that's what the snowball is the animal model for, is being able to move in synchrony with the beat. So I know you're talking about that there's a lot of synchronous vocalize.
Be sound, like fireflies.
Yeah.
They're doing it with light signals.
Yep. No, I totally get what you're talking about, but this is specifically about movement, and so the question that's being addressed in this literature is about how do people, the snowball thing, how do people synchronize movement? And so again, the typical model is some kind of external signal. By the way, the reason why I brought up bipedalism is because if you look at the only other, this is kind of a separate thing, but connection between music and movement, the only other animal group that creates melodies, kind of like humans, is birds. Like songbirds, and they are bipedal as well. So I really wonder if there's a connection there between bipedal stance, not on entrainment, but also the ability to vocalize melodically. So again, I know not much more than that, but that's sort of the other major group that creates melodies like us, and they are like us, and their ancestors, the dinosaurs, they are bipedal. So I didn't really answer your question very well, but I do want to think about this as being entrainment of movement and not vocalizing and not flashing, which are kind of different.
There's dinosaurs that are not bipedal.
Sorry?
There's plenty of dinosaurs.
Yeah, but I mean, let's say birds, for the most part, are
Okay, wait,
bipedal.
Laurel, you can have the last question. We're out of time.
Yeah, we're out of time.
Thanks, Stephen. So many interesting ideas. I wanted to go back to the beginning of your talk about the larynx
Yeah.
area. And you sort of started with that as a given. So humans have this larynx area, and then you derived, these really interesting ideas from that. But why would it have migrated there? Like, what were the evolutionary pressures?
That's a whole separate,
Why did it
yeah.
evolve with those capacities
Yeah.
and not other capacities?
So the question of why there would be a whole separate talk, so I've kind of addressed that a little bit, and I think in general, bringing the voice close to the other effectors for vocalization creates kind of like a short path for interaction at the brain level. So bringing the voice next to the lips and tongue, where it wasn't in non-human primates, I think would facilitate the coordination to create things like speech. But there's a lot more to the story about why did it go there and not some other part of the motor cortex. But I think going next to the lips and tongue is something for reducing path lengths, for creating this integrated vocalization with speech, where you have to move the lips and tongue and jaw together with activating the larynx. So that's a whole separate question about kind of why. What was the other part of your question? So why there and?
And why the capacities it has? So you're saying, it's limited ability to produce pitch accurately. So why would it have evolved that way?
Yeah, I mean, so that's not just about the brain, that's also about the larynx itself. And so that obviously reflects features of the larynx as an end organ, and then the other thing would be its innervation by the brain. So some combination of those two things is leading the voice to not be like a violin and to be much less precise than the instruments that sort of go into the standard theories of scales that are very perfect and very precise. But the voice is really nothing like that.
Okay, well,